Welcome to today's NFDI talk. This episode is about NOMAD, a distributed platform for RDM in materials science. Today's speaker, Dr. Markus Scheidgen, has a background in computer science. After several years of postdoctoral research in model-driven software engineering, he joined the NOMAD Center of Excellent Horizon 2020 project in 2017. He's leading the development of NOMAD and is the infrastructure coordinator for the NFDI consortium FAIRMAT. So the floor is yours, Markus.
Yeah, thank you. Thank you very much, Natalie. And thank you also to the audience for coming and listening to me. And I guess also for the people on YouTube to listen to this. Yeah, the presentation is going to be about NOMAD, which is the main service or the core service that we built in the FAIRMAT consortium. And as Natalie already said, I'm the infrastructure coordinator for FAIRMAT. We will later learn what this means. So the talk will also be a little bit about FAIRMAT, not just about NOMAD, but you will also see that FAIRMAT and NOMAD, they are pretty much the same thing. So this is the agenda for today. Like first, I want to talk a little bit about our problem domain and where the word FAIRMAT comes from. So it's going to be about fair data and material science. Then I want to highlight a little bit the FAIRMAT internal structure, like how we govern the project and how we work in the team and so on, because I think it's a little bit different to what usually happens in these kind of large scale academic projects. So it might be kind of interesting. And this is also the reason why FAIRMAT like basically mainly focuses on NOMAD, which is then the rest of the talk will be about our service NOMAD. And yeah, NOMAD is this research data management platform that we built for material science, and like an integral part of it, or two key tenets of NOMAD, is that first it's based on structured data, and the other thing it's like an extendable framework where people can build plugins for. So I will talk a little bit about these internals there, and then show you a few examples what you can do with the system, like how you can utilize this kind of structured data and plugins to do certain things with NOMAD. And then in the end, there will be a summary of the whole thing. Okay, so let me start with talking about the problem domain. Like first, material science. Yeah, material science is always a little bit problematic because in the context of NFDI, there are multiple consortia that do something in this field. So like more specifically, FAIRMAT is about the condensed matter physics and the chemical physics of solids. Yeah, there are other consortia like, I don't know, MATWERK, for example, or NFDI for Chem or NFDI for CAT that do certain things in a similar space. But from our perspective, material science is usually about there's this large space of potential ways how you can arrange atoms to form solid materials, right? And yeah, material science basically is about exploring the space, describing the space, and figuring out what are new materials with interesting properties that we can use in day-to-day applications. This is then where all the pictures here at the frame come into play. Like there's certain fields of applications. Usually it's like always like there's lots of things where we have figured out the physics, but it's just the materials missing to make it work, right? So if you ask yourself, why does my Tesla need like an hour to charge, or why is fusion always 10 years away from now, right? Then this is usually not because we don't know how it works. It's usually that we don't have the right materials to make it work. So we are looking for good materials with good properties. And these are some areas of our of application. We will later see when we look at the FAIRMAT use cases is what these are in detail. So this is like one way of looking at material science, and it's also the historical way, like how did this evolve over time? And in the beginning, there was like empirical materials research, right? So people just putting stuff into fire, taking shiny stones, heating them up, and see what happens. And this is where we get all these ages from, right? The Stone Age, the Bronze Age, the Iron Age, and so on. Like usually, whoever had the hottest fire could make the nicest materials. And then at some point, humankind developed mathematics, right, and was able to formulate models based on the observations made. And then if you take the computer into the equation, you can take these models and basically make make predictions. So this is where the computational paradigm comes into play, and we start to simulate materials. Or if we look at microscopy pictures and stuff like this, it's usually some sensor data that is then augmented with a model that makes it possible for us to see things that are not really visible by the naked eye otherwise. And through this computational paradigm in the last, let's say, 50 years, we already accrued like lots of data in this field. So there's lots of simulation results. There's also lots of experimental results. So we have this huge stock of data, and then the idea of data-driven research comes into play. What can we do with this data? How can we amass more data, and so on and so forth? And then this is, I guess, where NFDI comes also into the scene, and where most of the consortia are doing similar things, right? So it's all about building the right data infrastructure to make this data-driven research possible, which on one hand means that we have to digitize all the data, but it also means that we have to make the data interoperable, findable, accessible, and reusable, what this whole FAIR thing is about. So let's look a little bit at FAIR data and how does this, sorry, I forgot something. With data-driven research, right, this is then the idea that we can automatically explore this whole material space. We can use AI to give us the right direction and look where are like potential new materials that are interesting for us to explore and so on. So it's all about automatizing and making it more efficient to explore this vast space of possible materials for our quest to find the next good materials for helping out our society and so on. Okay, but now let's really look at FAIR data and how does this problem look like in our domain, in the material science domain. On one hand, we have lots of this, right? So lab notebooks is like the keyword here, often still hand-driven, or if you think about paper publications, it's similar. It's maybe not handwritten, but in the end, it's like text that contains the actual information. Nowadays, there are often like these electronic versions of notebooks, right, where people write down their observations and whatever they did in the laboratory. Now it gets digitized, right? So we have it in a digital form, but it's still not really accessible by a computer or by a search engine or whatnot. Because the information is still hidden in some English prosa. So there's a little bit more structure to it, but every notebook looks different, and so on. Exit tables is another popular kind of tool that is used a lot in the field. Now the data gets a little bit more structured. So we have like columns, for example, and we have column headings, and maybe there's a unit name hidden in the column heading. So there's some more information about the data, but in detail, we still have lots of problems, right? Nobody standardizes these kind of columns, and nobody makes sure that people actually use the right unit in the right columns and so on. That numbers are actually numbers and not some weird things. And completely different field is like when we look at data that comes out of instruments, that comes out of simulation programs, then we often have something like this, right? It's proprietary formats, like some tool vendor or some simulation code developer just devised the format, right? Usually it's like these kind of ASCII things where all the information, all the numbers are hidden in. And if you want to make sense of these numbers, you usually have to build your own tools to parse this and somehow get to the gist of it. And this is where FAIRMAT and FAIR data people want to do it differently, where we would say, okay, let's use like a more structured approach. This is here 2 screenshots of the NOMAD service, where we basically produce these kind of templates, right? These schemas, where every piece of information has its place, and it's then easy to find and use the information. And we will later see how this works. But this is the landscape that we are in, and we basically want to transition from these kind of paper notebooks and lots of heterogeneous proprietary formats into a more structured approach where all the data are more homogeneous and easier to use. Basically, where we have FAIR data. Okay, before we dive more into what we did with NOMAD and how do we make data fair and so on, I want to talk a little bit more about FAIRMAT, our consortium. This is a slide I usually use when I explain this to people that are not from the NFDI space to give them some context, right? So you all know we are one of these 26 consortia from the NFDI. So it's not just us, right? But every one of us is like basically dealing with a specific domain, and for us it's like this material science thing. And then there's a service that we build, like a product that we have, and this is NOMAD, right? A web-based service that you can use to manage your material science data. So this is how these things are connected. And now if you look a little bit into the internal structure of Fermat, I think this is also not new to you. Most of the consortia are structured in some kind of area or task area pattern. So we are no different here. We have like different task areas. On one hand, we have let's say the domain specific, the topical areas, right? So we have something about material synthesis. We have material experiments, and we have computational material science. So these are our areas A, B, C. I think the best way to explain it is to start with computational material science. These are usually the forerunners, right? So these are the people that are doing all the simulations. They're basically doing high throughput workflows, trying to explore the space of potential materials as quickly as possible. So they are the first that say, oh, this material might be interesting or that material might be interesting without even knowing whether this how this material actually would be made to come into existence, right? This is then where the synthesis people come in, where they say, okay, this sounds interesting. Let's try to see whether we can synthesize this material, and then they are creating samples and stuff like this. And this is then what people in the experimental realm can put under the microscope and figure out whether this sample actually fulfills what the theory was proposing. So this is where techniques like looking spectroscopy and microscopy and whatnot, like looking at the inner workings of the material and get some knowledge this way. So these are our topic areas, and as you see from this narrative that I'm trying to put out here, that these areas they are connected, right? And they would greatly benefit if they could freely share information and collaborate in such a way. So this is also then one goal of Fair Data and of NOMAD to bring these all together. And we try to show how we can bring them together in the use case area, where we basically picked certain applications. And then based on these applications, try to tell how NOMAD can help and connect the various branches of material science to make databases for certain material applications. And these applications are stuff like batteries or solar cells or catalysis and stuff like this. Yeah, so these are our topic areas, and they are basically NOMAD users, right? So the people that work here, they take the NOMAD software and then they try to adapt it, right? So they know their specific domain, they know the people in the field, like the researchers that work in the labs, and they basically talk to them, and then they say, okay, with NOMAD we can improve the situation like this and that, and then they build plugins and so on based on our platform, and they're basically bringing the system into the laboratories. And the idea here is to create good examples, good use cases that show the potential of fair data and how we could use a system like NOMAD to drive the adoption from there, right? So showing that this is more efficient if you use this, and so on, and then hopefully inspiring more and more people to do the same thing. And then the other area that I haven't talked about it yet is the infrastructure area. This is also where the name infrastructure coordinator comes from. So this is basically my area, so to speak. And this is where we build NOMAD, right? So this is a core set of developers that builds the platform and makes it usable to the others. And then we have also an outreach and training area, and an area that coordinates, does HR and stuff like this, and sees over the budgets and so on. Yeah, so this is the inner workings of Fermat. And yeah, what we try to do is to build like this kind of distributed architecture of NOMAD. We will later see like NOMAD comes in like different flavors. There's the central NOMAD, which is what most people associate with NOMAD. I guess this website where you can go to, and then you can look at all the material science data. You can upload more data. You can publish your data and stuff like this. But as I said, we also want to build like an extendable platform, a platform that you can change and where you can build plugins for. And this is where the NOMAD Oasis comes in. And this is the idea that people take the same software, they install it locally in their laboratory, and then they adapt it, right? They connect it to their microscopes, they connect it to their HPC systems, they apply their own policies on top of it, and so on. And this is then what creates this kind of distributed network where the different partners basically can contribute their own hardware, their own infrastructure to the network, run our software, then to drive the workflows in their laboratories, right? So this is all about connecting the different stuff that you have in your lab, and then eventually either completely or partially transferring the data to a central system where we then can see over aspects like longevity and then publishing it and so on. And the idea is that, like, in the end, the broad community can use the central NOMAD as a portal to then explore all the fair data within the network. These are our main goals or principles, how we want to drive this. Like FAIR, I think everybody is aware about. We also want to build an open platform, which I guess is not surprising. So everything is like open source and free to use. But open for us means also that we basically want to produce a process that is kind of open, where everybody can contribute their data formats, for example, or their data standards and so on. This is then also where the plugin idea comes into play, and where lots of our outreach is going towards, like where we try to create, for example, we have a Discord server where everybody can be a member and talk to us, and so on. Yeah, and the other key ingredient is this bottom-up approach, right? So we basically look at our space and we see that there's lots of file formats already there. So what we want to do is we want to accept this diversity, right? And we still want to make it work, right? So it's more about taking the information as it is and converting it into something that is more homogeneous and easier to compare, instead of creating just a standard and then imposing it on everybody else. Yeah, so this really is based on the belief there's already lots of stuff there, and we need to make it happen with the ingredients that we already have. So this is the bottom-up idea. Yeah, this is the team. This is what we look like. I think you have an idea about the scope of an NFDI project because you run your own. So we are basically something like 60 PIs and 30 co-workers. Here you see our speaker, Claudia Draxel, here in the middle. And then here, this is me, for example, right? And if you look at the front row, these are all people that we call coordinators. And then in the back row, you see all our PIs and our other co-workers. And the idea here in this structure, and where we might be different from what you typically see, like in a big academic project, is that we are not really allocating our co-workers to, let's say, to individual PIs and govern it like this. It's more that we use the coordinators as a middle layer to organize stable teams and to work consistently on the service, right? So we basically have the top layer with all the PIs in it. So we have area leaders and we have leaders for the various tasks and so forth, like experts in their respective fields. They are then basically the people that try to devise the strategy, what topics are important, what topics are less important. They also have the network to basically tell us there are great laboratories, they're doing great stuff. This is where we should try to get into, and so on. And then we have the layer of coordinators, right? So every area has a coordinator. And then we have some special coordinators like the infrastructure coordinator, the scientific coordinator, and so on. And the idea is that these people are then governing the domain experts and the software developers and so on, the actual co-workers that we're having that do the real work. And the benefit of the structure is that the coordinators can create stable teams that work together. We mostly are all sitting in Berlin. This is also where this picture is taken here. This is like our CMSB, that's the institute where we're sitting in the Adlershof campus. So we are all together and we can work together on a day-to-day basis. And we are basically working on similar goals that are somewhat aligned through the coordinators, right? So it's not everybody's just doing what his professor wants. It's more like everybody's doing what the project wants. Yeah, and this is also how we manage to keep everything together under the NOMAD umbrella, right? So it's basically more or less every one of those employees is working on NOMAD and on this one service in one capacity or another. Okay, but now enough of Fermat and our internal structure. Now let me get to the actual gist of the talk, and this is NOMAD and what it is and how it works and how you might use it. So this is what, from a user's perspective, people usually see first. This is like our homepage. And here you can see, okay, it's about sharing material science data. Here you can also see already some numbers. So this, yeah, I think this tells people that this is not just a PhD project, right? There's really a service there that is used by people. So we have like the numbers not even correct anymore. It's like now 13.5 million or something like this, different entries in the database, respective file size covered and so on. So here people learn about what the platform is and what it might do. Here they can also see that we come in these two flavors. There's also the NOMAD oasis that people can use to create their own customized NOMAD and so on. And then at some sooner or later, people click this button here and they jump into the actual application. And this is where they then see the central NOMAD and all its data. So it comes with a search interface. It's like this kind of faceted search where you have like a very extensive menu with all kinds of filters that you can create. And then the filters are spanning things like the periodic table, of course, but then lots of stuff about the employed method, about the calculated or measured property, and so on. We also have these kind of dashboards. We will later see like a more extensive example of this that allow you to get a grasp over the space that you're looking at. We are basically plotting certain properties against each other, and that gives you a better idea what the whole data is about. And then when you start clicking, you're basically zooming in and creating these funnels until you arrive at some data that looks interesting to you. And then if you click on individual entries in the database, you get a page like this. And this then really depends on what type of thing you clicked on. In this case, it's like a simulation, a DFT simulation. Then you basically see the system that was simulated and then some properties that were calculated. Yeah, and then you can even go deeper. And then you see the underlying data structure. Like for each of our entries, we have this kind of section-based structured data hierarchy. So in this case, it's a simulation. So we have a simulation run. There's a system that was simulated, right? And the simulated system consists of atoms. And we see the atomistic structure. The different positions of the atoms is then like a 3 by whatever matrix of atom positions and so on. And this is not just for the atom positions, right? This is what we have for all the properties that are involved in the thing. So one individual entry might contain of 50 to 200 or whatever different data and metadata points. And all these data are there. They have a formal schema. So there is a name for them. There's a English description for them. There is a unit, right? And the data type and the shape. Potentially also a connection to an existing ontology and so on. So this is then all stuff that allows you to understand the data. And this system, this is what I usually call structured data, and this is then the basis for all the fairness of the data, right? Because now we have these individual points that we can put into our search index to make the search happen. This is then also stuff where it becomes like easier to access the things because we can build APIs around it, right? And you can grab each of these individual entries as a JSON document, for example. This is also what makes it more interoperable because we use the same kind of schema system and the same way of structuring all the data. So we're basically going away from individual files. It's not about sharing files. It's about sharing data and information, right? And then eventually this is then also what makes this reusable, right? Because now humans and machines alike have a better understanding of the data and can do more with it. And with the structured data approach, we can also track the provenance and whatnot. Yeah, this is the core of NOMAD, and around this we built lots of tools. You already saw the search interface. Another thing that is very popular is what we call North. That's the NOMAD Remote Tools Hub. It's basically a Jupyter hub that runs certain tools on top of the NOMAD data. So for example, this allows us to run Jupyter notebooks where people can then programmatically do something with their data. But in this framework, we can also run other containerized tools, for example, desktop applications. So this can be certain analysis software or maybe instrument control software, whatever you can directly run in the browser, and in the background, everything is connected via APIs and shared file systems and so on. So it becomes very easy for the scientist, like if the NOMAD is set up in a good way and there are plugins in place and whatnot, basically the whole workflow can happen in the browser, and they can do everything from there, and they don't have to deal with like installing this, installing here, and so on. Yeah, this is the user's perspective of NOMAD. Now I want to go a little bit into the details how this works internally. so that you can understand the system better and why we think it works so well. The key part of NOMAD is, on one hand, it's basically just like typical Dropbox functionality, typical file sharing, right? You can upload your files, you can create directories, you can create projects, you can put more data in there, you can share it with other people. Like, this is like pretty standard stuff that you know from most cloud kind of environments. The big difference in NOMAD now is that NOMAD then also processes the data, right? So at every file that gets uploaded, we look into the file, and then NOMAD tries to understand, yeah, this is a file format that I know, this is something that I understand, this is something I can pass, and then NOMAD is automatically converting this file into these structured data, right? So for example, if I upload a simulation file, there are certain file formats out there that come from the code developers, right? Then NOMAD understands these kind of files, extracts all the information, and extracts the method that was used, the system that was simulated, the properties that were calculated, and so on. And if you put in like some experimental results, something that comes out of a measurement device, then it might be the same thing. The information that is produced is different, right? Now it's about the instrument that was used and the settings on this, right? It's about the sample that was put into this thing. It's about the whatever was measured there. But the principle is the same, and the schema language is the same. It's different schemas, but it's the same system. And then on top of this, we can further try to deal with this. There's still some heterogeneity left, right? But then we can also try to deal with it and identify what is common among these entries, right? So in the simulation, you were calculating some property. In an experiment, you were measuring some property. Then we can create this kind of material layer or layer of material properties where we really then say, okay, there was a property simulated, there was a property experimentally derived, and now we basically put them in a schema where they become comparable. Yeah, so this is our structured data approach, and then, as I already said, this is then the basis for everything else. This is what then the search engine, the APIs, and everything is driven by. But the core loop is very simple. It's just about there's a file, you process the file, right? You open the file, you understand the file, and then you produce structured data from it. And this is then also where our plugin mechanism comes into play, because this is then what you can extend. You can write your own parsers for your own file formats. You can add your own schemas. Basically, these kind of things you can define yourself. And then you can also add additional processing functions to the system, right? So you can program into the system something like, if the user enters this and that, and if he attaches a file like this, then please open the file. Read out the file, do something with the file, and all these kind of things you can put into your plugins and then automatize the process for the end user. I had an example for this. Let me jump to this. Yeah, here, for example, we see something like this, right? So there's something like an ELN in the NOMAD system where someone defined the structure and all these kind of form fields that you see here. And then the user uses them, and he, for example, uploads a file, and then the file is associated with this entry. And the plugin beneath basically tells the system, okay, open the file, interpret the file, create this plot from the file, and then the plot suddenly appears in the front end. And this is then in the end a very powerful system, because you can create all kinds of different forms and all kinds of different actions based on this. And this way automatize the workflows that you have in your lab and so on. So now let me jump back to my original plan. Maybe one more minute on structured data, and then I move on. So the idea and what I tried to show you with the screenshots before, we have these kind of structured data in the middle. So we have this hierarchical data layout that is governed by a certain schema. And then this is what makes a lot of NOMAD happen, right? So this, for example, on one end means that we can upload all kinds of things and we can interpret all kinds of data. So this can be files that are uploaded that are using one of the supported file formats. Again, this number is outdated. I think it should be 75 by now. So we have parsers for 75 file formats that are where the data gets then interpreted in a certain way. We also support other kind of data standards that govern multiple formats, so to speak. Like Nexus is one of them, which is pretty popular in the experimental space. But Nexus is not just one file format, it's also like something where you can define lots of different things in there. So that brings in like support for another 40 kind of file formats, so to speak. We also have some facility to deal with exit tables and for CSV files. Like this is in the synthesis world used a lot. And this again, like then in our plugins, there are like specific routines that interpret like Excel files and CSV files in a certain way. This brings in another 40 file formats and stuff like this, right? So this allows us to support like lots of different data, which is great for the end user because he just needs to drop the data there and then they can do something with it. We are also working on integrating with other databases and other electronic lab notebooks, for example. So for eLab FEW, for ChemMotion, for OpenBiz, for LabFolder, for these kind of things, we basically have import functionality that basically takes their file format and then extracts the data like this. We have also some native formats that our UI uses for all these form fields where the user is putting in information and stuff like this. This is where this is used, right? This is how the information also gets into this kind of structured data world. Another aspect is like how these structures are defined. This is where we have our own kind of schema language, which comes in two flavors. You can program it in Python, which is great for our plugin developers. You can also describe it in YAML. It's less powerful, but this allows people to basically just upload their schemas, and we can make it a little bit flexible, even without creating your own oasis, without creating any plugins. You can still define your own schemas, extend the existing schemas, and so on. Yeah, I already talked about Nexus a little bit. Nexus comes with their own kind of schema description definition language that we now support. We are working on integrating this into the world of semantic web. Like how can we take our schemas and translate them into RDFS or into our schemas and stuff like this. On the bottom edge, we have like the data storage. Like most of the information in NOMAD is file-based, so we store all the files that are uploaded as files, obviously, but also the process data gets then stored in some binary flavor of JSON. Here we are also working on supporting more efficient file formats for bigger data, like HDF5, for example. And then also some of our data for efficiency reasons is stored in databases, like in Mongo databases in our backend and also in Elasticsearch. And you can imagine that Elasticsearch is then what drives the search engine and so on. And on the last vector, so to speak, like how you access the data, structured data is also like helping us a lot. So this is basically what we structured our API around. So you can access the data in a structured way, and then this allows it for us in the UI to drive all the visualizations, to create all these kind of plots. People can create their Jupyter notebooks, access the data like this, and then apply machine learning methods and stuff like this on top of it. We have some built-in library functions that allow you to take the NOMAD data and translate it into NumPy arrays, into Panda data frames and stuff like this, so that it becomes easier for you to work with this. And this is also where we are working on connecting this to the world of semantic web, exposing all the data, for example, as RDF documents and stuff like this. All this is also where you could try to integrate with your own database and maybe just download data from NOMAD and put it into a different system and so on. Yeah, so this is our structured data approach, and NOMAD is basically built around it. And lots of the stuff that you see is basically based on this on the system. Okay, now let me jump to our to the part where I wanted to talk about what you can do with NOMAD. And here, let me start by talking about the search interface and the ability to define dashboards and your own search apps for your own kind of different data types, so to speak. We did this already for like a few application areas. So if you go to NOMAD, like this is a screenshot of NOMAD, right? And if you go to the Explore section, you get this menu where you see all our different search interfaces, so to speak. And this is what we call search apps. So there is a search for looking through DFT calculations. There's a search for looking through like materials derived from these calculations. There's a search for ELNs. There's a search for like a specific type of experiments. There is a search for metal organic frameworks and solar cells and so on. Like this, and this is something that we want to extend on, right? This is basically where our use cases come into play and where we want to show examples. Like this is what the solar cell database could look like. If you have your own application and your own idea, you can follow this example, right? And you can create within NOMAD, you can create your own database with your own search interface where you represent your data in whatever way you deem necessary for your community. Yeah, and what I want to show you here is like the solar cell app, right? So you click on the solar cell thing, and then you get to the solar cell search app. And here you see what I mean with this dashboard, right? So you see visualization, different pieces of visualization that try to explain to you what all the solar cells look like what does the search space look like. So at the bottom, we have like this here. You can't see the rest of it, but it's basically a giant table of all the solar cells that are in the system. I guess like 43,000 solar cells that were derived. There was like a longer ongoing project where people were basically reading through existing paper published materials and try to homogenize all the data from all these paper publications about solar cells. And they basically ended up with like a giant Excel table with these 43,000 rows in it and 400 columns in it. And these columns were then things like efficiency and blah, blah, blah. All these kind of things that are describing the respective solar cell material. And we basically took this Excel table, converted it into NOMAD data, and then what you see here is basically every dot here, right, is a representative of one of these rows, one of these solar cells. Or solar cells get categorized into these kind of histograms, where, based on how the solar cell device was created or what kind of layers were used, you have like different pieces here, and then of course you also have the periodic table. You see the elements that are involved in these materials and so on. And the thing about this is that this first it gives you like a rough shape about the data that is there, but it also now allows you to interact with the data, right? So you, for example, I can take this and I can zoom into this part here. And then if I do this, like if I zoom into this, I basically create a search filter, right? I now say I'm only interested in the solar cells where the efficiency is between here and there, between there and here, and where the open circuit voltage is between this and that. So I zoomed in, created a search filter, and with this search filter, obviously everything else changes as well, right? So the charts changed here a little bit, this changed, and so on. So these plots are connected with each other. And if I create more filters, so now I clicked a few elements, for example, the thing changes again, and I create more filter, and the stuff changed again. I now added here a range, for example. Now I select a few categories here, and so on. So the data gets smaller and smaller. And this is how you can explore the search space, right? And how you can explore different relationships between the things that are plotted here and so on. This is what we mean by search apps. And the thing is that this is nothing that is like kind of hard-coded into NOMAD. This is something that people can add themselves, right? This is where we are talking about plugins. So we are doing regular tutorials on this, and there's also documentation on this and examples and so on. So basically, we ask our community, if you have data like this and if you want to have something like this, follow this tutorial. And then they can basically define their own schema, how their data is structured. And then they can say, okay, I want to plot this property over this property, and I want to plot this over that. I also want to have the periodic table, and these are the elements that I have in my data, and so on. So then they can create their own filter menus, they can create their own dashboard. And with this, they basically can create a database within the database, right? So within the normal platform, they can publish their own data, and then also make it visible in the way that they think is the right way for their types of data and their community. So these are the search applications. Another example I wanted to show is normal camels. This is a framework for automatizing your laboratory, in the sense of that you want to control your instruments and drive measurements and stuff like this automatically. And camels is basically a system where you define a measurement protocol, what you want to measure, how often, in what order, and so on. And then basically NOMAD Camel takes this, translates this into instructions for the instruments itself, or it goes through a framework called Epics, which is then also about automatizing instruments and so on, and measuring the environment and so on and so forth. And then with these two systems, it basically does the experiment automatically and collects all the data that gets measured and so on, puts everything into structured form, and then stores this in NOMAD. And this is for us a great way to start automatizing the lab, right? So there are lots of people that do this to various degrees, up to laboratories that are completely automatized, right? Where the sample is created, the sample is driven around on the conveyor belt, some measurements are done, the data is taken, it's analyzed automatically, and then based on the analysis results, the machine decides, okay, this is the next experiment I'm trying to do. Now I'm mixing the chemicals a little bit differently, and then so on and so forth, right? So this is the idea where the community wants to go, and we basically want to support the different building blocks here, and lab automation, controlling your instruments is like one aspect, and this is what we are covering with NOMAD ChemAds. It's basically another part of the NOMAD service, so to speak. But this also shows how we believe that it's easier for people to adopt the whole system where everything comes as one service, because you basically go to one place, and this is where you do all of the stuff, and where you also get informed about all the possibilities that you can do. So we are basically doing the integration work so that the laboratories don't have to do this, right? Because otherwise you use one tool here, one tool there, then you are stuck with two different file formats, and you have to do the work, how to combine this stuff and stuff like this yourself. This is basically what we want to take out of the hands of the scientist, and this is one of the reasons why we think, like, let's provide a service platform that combines the different aspects of research data management, instead of having individual services that then people have to stick together somehow themselves. I think this is my last example. This is workflows, which is another very important topic in many of the NFDIs, many sciences. Material science is no different, right? So what we do in the laboratories usually follows some kind of recipe, some kind of workflow that we then also want to track. And with our structured data approach, it's very easy to come up with a schema for workflows, right? Where you say a workflow consists of tasks, and then these tasks are connected with each other, like one task comes before another and so on. So it's very easy to model something like this, right? And then you can write your plugins in a certain way that that you use this model, and then the different points get connected automatically when you do something. This can happen in like these kind of automatized lab work, for example. So if you use NOMAD ChemAds and you do different measurements on the same sample, it's very easy for NOMAD ChemAds then to use a workflow model and connect these kind of things. It's also very prominent in computational material science, where things is often a sequence of different calculations to come to unified results. And the important stuff about the workflows is that we want to know the workflow, right? When you look at the data and you look at a certain data point, you want to know how this came to be, and what was the sequence of steps that were taken to actually arrive at this data. And this is then based on the model you see in the background. We then implemented something in the UI that shows the data according to this model. So if you look at at some final calculation result, for example, then you see what other calculations have been necessary to get there. You can click all these elements and jump to the various entries in the database to see what was happening here. And in the end, you have a track record of the full provenance of the experiment, or of the simulation. So it's very good to have like this kind of workflow support in there. But this also shows a little bit what you can do with structured data, right? So in my model here in the background, we have the blue part and we have the black part. So the idea is the blue part, that's something that normal people can predefine. Yeah, that's basically like a standard where we say, okay, this is how we want you to do your workflow. And then when people create their own schema, they can do the black sections here, and they can basically have their own stuff added to it that uses the workflow. Which then means that NOMAD can build something about the blue model, like this workflow visualization is just based on the blue boxes here. So whatever uses the blue boxes gets this picture. And people can, at the same time, they can extend this, right? They can inherit, they can create their own workflow, and they can basically then reuse this kind of work that we did for them, right? They can reuse this visualization and depict their workflows in a certain way. This is what we call base sections in NOMAD, and basically we have whole libraries of these kind of base sections that are covering certain commonalities between different aspects of material science. This is where I also have this picture here. So the people are often asking, if you allow people to write your own schemas, like how do you prevent that this doesn't create like a complete mess where everybody is creating their own schema and structuring the stuff differently? And this is where our idea of base section comes into play. So there's certain base sections, like rows and these kind of screenshots that I showed, where we say these are predefined, these come directly from NOMAD. The workflow, for example, is something like this that can be predefined, or other concepts like what is an activity, what is a measurement, what is a simulation. You can have a very high level understanding of this notion and basically create a shared definition for this. And then people can build their own plugins and they can say, okay, now I have a special simulation. I have my vast simulation, or I have a special kind of measurement. And users that use these plugins can go then even deeper and say, okay, I want to still specialize some more. I have more properties that I need to add to this. There's more details that I can give that were not covered by the more abstract example. And this is basically the system that we put out so that we hope that we can drive some consensus and make people use the same system. But of course, people don't really like to use things that exist for some reason, and often people want to define their own stuff and so on. And this is then where the ideas like the workflow visualization come into play, right? The workflow visualization provides some value. If you use the blue boxes here like a good citizen, then you get this. And if you do your own stuff, then you can't profit from this, right? So this is how we create incentives, so to speak, for people to reuse the existing definitions. So we don't really want to define a standard and just say you have to use it, but we say, okay, here is something like a standard. If you use this, we can provide you with specific tools. You become more interoperable with others and so on. And then it's not just something for the community to benefit from, it's also from the individual, right? The individual can say, okay, now I get this visualization, now I can get the visualization. I don't have to do it myself. This gives me some immediate value. So I might care about the system at large, or I might not care. I'm selfish. I get something for myself, so I do it. And I think this is like a good building block to have to do this bottom-up kind of a system where we try to drive something from the community upwards. So now I'm running out of time. Let me jump to my summary here. So I was talking a lot about Fermat and NOMAD. I think the things I want to stick is that NOMAD tries to create fair data. We are an open platform, and we do this bottom-up approach, right? We're really are embracing that there's diversity and that there are different file formats out there, and we try to basically adapt them and combine them. And the means that we're using for this is like structured data, right? It's building schemas, building plugins, and so on to consume all this information and make it more homogeneous and make it fair in the end. And in the process, we are trying to build this kind of scalable architecture, right? You have this distributed component to it where different institutes can contribute with their own oasis. And it's also an extendable infrastructure. People can build plugins and they can basically take the core NOMAD and build more stuff and more applications around it. Here you see a nice picture. If you maybe have more time later on, you can try to look at some of the numbers, some of the key numbers I already mentioned. But for the sake of time, let me go on. If you later look at the presentation, I'm sure we are sharing it somehow. There are a few links if you want to learn more about NOMAD. There are also a few links in social media tags and whatnot if you want to learn more and keep up to date about Fermat. And that brings me to the end. And I think we wanted to do a discussion round. So thank you for listening. And then I'm open for your questions.
So thank you very much for this interesting talk. It was really insightful. And with this, we say goodbye to our audience on YouTube. In our next episode of the NFDI talk on 21st October, we will have a talk about AMPL, a fair analysis engine for high throughput heterogeneous data streams. And